Thank you. Thanks for inviting me again. Yeah, that makes my life harder because I need to make a different talk, so I don't need to explain the same things. Although I imagine the audience is not familiar with quantum and has different background, so it will still be quite different from last time, but it will be a bit high level talk. Okay, so this talk will have three parts. The first part, I'll just say briefly a few things about quantum computing in general. Then I'll give the state of the art, so where we are with quantum computers, because I guess you've been hearing things in the news, so and you may wonder where we actually are, and have a more sober view of where things are and going. And then the third part is more relevant to the theme of the conference, is about evaluating quantum computers. Here, not quantum computation, because I'll tell you a bit about how we evaluate the hardware as well, and things about evaluating the quantum computations and quantum software as well. Again, caveat, I'm not an expert in the form like quantum software verification, so I'll say the state of the art and some other results as well. Okay, so the first part, I'll start with what a quantum computer is and what is not. Then I'll say a few things about quantum hardware, errors and the challenge of fault tolerance, which becomes relevant for, as you'll see, both in terms of how it delivers advantage and in terms of how complicated things are to test eventually. And a few things about known algorithms and the QD, and where what we know that quantum computers can do. Okay, so a quantum computer is a device that can manipulate in a programmable and fully controllable way quantum information. So basically we have systems that now instead of classical bits, we have quantum two-level systems that are called qubits, and they have different properties. So they have very different properties, and because they have these different properties, the algorithms that you can run with those qubits are different than the algorithms you can run classically, and you define a different computational model. And in particular, things that are hard for a classical computer, they may be easy for quantum, like hard now in the complex theoretic sense. So you can have things that maybe are not solvable in polynomial time classically, and they become solvable in polynomial time quantumly. But also in a less strict sense, you can just have speed ups, basically, that they not necessarily are exponential separations. Now, before we go, I mean, that you must know that a large-scale perfect quantum computer does not exist. So, all the things you've heard is like we're moving towards that direction. As I say, progress has been made. And in particular, for many years, when people ask us, okay, so when you'll have a large quantum computer that can do things, I mean, everyone was saying in 10 years. For 30 years, they were saying in 10 years. So now this has moved, and it's maybe in 5 years. So that's an improvement. We don't know in how long we'll still be saying in 5 years, but it's a progress. Okay, right. So the main idea is that like qubits, I mean, I explained that in 3 years back, so I'm sure everyone remembers that. But so the most characteristic property is that qubits behave as having complex valued probability. So you can think as generalization of probabilistic algorithms that instead of like numbers between 0 and 1, you take complex value, you take complex numbers. And this, of course, means that you can have strange things like the probability of something being positive, the probability of something else being also positive, but the probability of the one or the other being 0. So this is something that is fundamentally different. And this is the concept of interference, and it's what basically brings the possibility of quantum advantages. That's why we have a different model. In a sense, we have a new way to run algorithms. So in other words, the speed up actually comes exactly because you exploit this type of properties, and you need to be clever and construct a different algorithm that uses these properties to solve things in a better way. And again, this means I spent a lot of time the previous time here. I'll just going to mention it doesn't mean that the quantum computer is just faster because, like the NOT gate happens faster than the classical NOT gate. Definitely not. Actually, if anything, they happen slower. So the gates, the operations are slower. It's not that you run parallel all the branches of the probabilistic computation and you just extract the outcome. People have this idea that you can run things superposition of states. That's not the case. Well, it is that you can run superposition of states, but you cannot just extract information about all the branches of the computation. You learn something about all the space of probabilities that you wouldn't be able to learn otherwise, but you cannot extract all this information. And therefore, there isn't a task-independent advantage. It's not that, okay, you give me the problem, I put it in the black box called quantum computers, and I give you a fixed, advantage. So that's not how it works at all. Having said that, BQP is a complex class of problems, decision problems that a quantum computer can solve in polynomial time, and it's a complexity class. So there exist problems that are hard that do not belong in BQP, and actually this is the conjecture relation with P and NP. So you can see two interesting points here are that there are things in BQP that are not in NP, and this makes the life more difficult in verifying if a quantum computation is correct, because you cannot, so you can definitely have things outside NP. And there are things in NP that are not in BQP. That also means anyone that told you, oh, we're going to solve polynomial time NP hard problems. Nope, we're not. We may get a speed up. So we may get, which might be really important, high polynomial speed up in some cases, but we're not going to have any polynomial time algorithm for NP complete or NP hard problems. Unless this hierarchy collapses, which will be, almost as drastic as P equals NP. Okay, so that's about what quantum computers are not. Quantum hardware, all these cool different technologies. So we don't know what systems are the best. So we know that you need to have a qubit, which is a 2-level quantum system, but it can be superconducting to like 2 degrees of freedom, or ion traps, ions in a trap, photons, quantum dots, neutral atoms. There can be any of those, and all these technologies develop, and all of them improve, and all of them have their advantages and disadvantages, which we're gonna see. They have its merits, and it's completely open which one will be the eventual winner. That's why all of these are developed. But for now, it turns out that for some applications, the one might be more suitable than the other, interestingly, because they have these different properties. So for example, superconducting qubits have way faster gates, order of magnitudes faster than ion traps, but then they have much fixed connectivity. So you cannot, you need to turn around, do many swap gates to interact with the qubits and so on. And you have worse quality of 2-qubit gates. Okay, so right. So when I say 2-qubit gates, errors, and so on, we go to errors and fault tolerance. This is another very important thing that people need to be aware when talking about quantum computers, is that quantum systems are super hard to control, and they have errors. So when you have this, you apply a 2-qubit gate, you are going to have error. Now, even if you have a 10 to the minus 5 probability of having an error when you apply a 2-qubit gate, which is not where we are actually, we are not there yet. For any of the reasonable quantum algorithms, not reasonable, for those algorithms that we know that there are exponential separation, you need to have hundreds of millions of gates, even billion of gates. So you can see 10 to the minus 5, it means that you'll end up with pure noise. So really, you cannot just do quantum computation like this. However, we can save the situation by doing this following idea. We can use multiple physical qubits. Let's say we get 10 physical qubits, and we kind of do some trick, and we encode the quantum information of one logical qubit on those 10 physical qubits. And we can do it in such a way that the error in this logical qubit is suppressed, and it can be suppressed as much as we like, essentially, to run the algorithm we want. Of course, this comes with an overhead, because now we have fewer, if we had 1,000 physical qubits and we need to spend, 10 for one logical qubit, which is quite ambitious, then you have only 100 logical qubits already. Okay. And how this ratio is this physical to logical qubit ratio depends on many things, including what error correcting code you're using and the way that you do the logical gates. But also, it depends on what is your error in your physical gates or your physical qubits in some sense. So you can improve or decrease the physical to logical qubit ratio either by in the theory side, so if you improve your codes or the way that you do logical gates, or you actually improve the hardware. I mean, I'm sitting in the quantum software lab in Edinburgh, so it's second half I don't know much about it, but I talk to our experimentalist friends, so they tell me things. Okay, so that's that. Okay, cool. And you have that quantum computer, so what? Well, in theory, you can get speed ups or better accuracy or even less energy. Now that we are in the era of big data centers and like AI, so energy consuming. You could in theory use quantum computer to not to do things better, but maybe to reduce the energy cost. So that's also one thing that you may have. And in theory, you can get speed up to all computational tasks. So like our recently funded big project has work in all those different sectors. But do we know how you get advantage in all those things? Actually, no, we don't. And that's why it's a research project. So these are, like for some of these we know, but for some of these we don't know. What we do know for sure is that there are two key algorithms that exist since the 90s, and we know known guarantees: source algorithm and Grover's algorithm. Grover's algorithm, you get a very this is the most generic quantum advantage you get, because you get the quadratic speed up in a search algorithms. And you get it, but you cannot get anything better. And this may have some implications for symmetric cryptography, but not so significant. And the other one is the one everyone knows, is you can, in polynomial time, factor and do the discrete logarithm, which means that it breaks RSA and other cryptographic protocols. And this brings me to the next thing I want to mention. I'm running low, so I need to speed up. Yeah, I never calculate the time that I need for things. So Q-day. Q-day is the day that for which a real quantum computer is powerful enough to break public key encryption, basically like RSA 2048 or these type of things. Now, source algorithm, exactly because it's it's polynomial time, but requires many logical qubits, requires a lot of error correction. And so you needs way more physical qubits than what's the logical qubits. And to calculate exactly how many of those qubits you need this resource estimation, that you need the quality of qubits and so on. But also to predict the Q-day, you also need to know how quickly the hardware will develop. So you have these two sides of the equation. There are plenty of factors, so I'm running low on time, but this Q-day can move for many reasons. It can move because maybe you find a better quantum factoring algorithm, not exponentially better, but even a small advantage. When we're talking about constant factors, this could bring the day way closer, and that's what happened earlier this year. That there was a result that basically reduce the number of qubits that you need for Q-day. So if you've heard, Google moved their date that they want to move to PQC, quantum cryptography, to 2029. Yeah. Better error correction methods. So these are these different LDPC codes that may offer you up to 40 times of fewer qubits and so on. So I'm not going to all this, but the point is that there is an interplay between many different factors for doing the resource estimation and predicting the Q-day. So that's that. So this is what quantum computing in state of the art. Okay, so qubits. I told you that we need many qubits. You understand that we need many qubits, but we also need error rates low. So the record of qubits is around 1,000 qubits, and the record for lowest error rate is 10 to the minus 4, but it's not in the same device. So it's not that you have 1,000 10 to the minus 4. The 1,000 qubits have 10 to the minus 2 error or something like this. But you can see here in this plot, you can see that there is the number of qubits, and this is the error rates. And you can see these dots are real quantum devices where we are. and this is what we estimate with existing algorithms and so on, where RSA will break is here, and here is other useful applications and so on. So this is an updated map that some Zags keeps updating. Okay, just a quick thing. Classical simulation. So the reason you cannot simulate classically a quantum computer is because you would require 2 to the n bits to simulate n qubits. If you just want to simulate a quantum program, if you want to solve the same thing differently, you might be able to do it in a better way. But if you just want to simulate it, you need 2 to the n, which means when n is 50, then you are done. You cannot do it with classical supercomputers. So there is no supercomputer that can simulate generic quantum circuits beyond 50 qubits. And initially, what people cared, like Google, the first like this in 2019, that result, they wanted to prove that I have a completely random problem that is not of use to anyone, but we can prove that our existing device can do better than any classical system. And of course, when you exceed the 50 qubits, you have a chance to do that. And that's what Google did in 2019. They had 53 qubits. But then it was rebutted by IBM that they say, okay, we can actually do that and so on. But then the recent ones, 24 and 25, now the device has better fidelity and way more qubits. This question has kind of been sorted that in useless problems, quantum can do better. So, and now the question is, okay, what about useful things? And that's what people now they moved from speaking about quantum advantage to quantum utility, which is what we moved to. So these are commercially or scientifically relevant problems, and there has been. So I'll give you just 3 examples that we are going closer to this. So the IBM had recently a paper that they actually did in their 144 qubit device, this 2D discrete time crystal, which is some properties of matter. Basically, they explored that with naive classical approaches you couldn't do. However, with naive classical approaches, they still don't claim that this is a quantum utility, but they are getting pretty close, and this demonstration is a very good step towards that. There was recently one of the big problems of using, there was a lot of promise of using quantum computing in data science. There were all these algorithms from the 90s, again, the HHL algorithm that provides exponential separation for some linear algebra problems. But the main problem in most of those family of algorithms is how to upload your data in a quantum computer before you can do the things with exponential. So basically this paper by Caltech and Google actually achieved an exponential separation, this QRAM loading. They solved, essentially they had the theory that they demonstrated that they can do this thing efficiently, and they actually implemented it with 60 logical qubits. They can store up to 10 to the 7 classical bits and in a way that it can be used later for quantum algorithms. A third one, this is one of our results, is but this has not run in a device, but we proved that with 160 logical qubits you can determine properties of graphene in scales way beyond what the most powerful supercomputer can do. But it's still 160 logical qubits is not where we are now. So that's this paper is like demonstrated this possibility. Okay, what about error correction? Again, this is probably the hottest topic, quantum error correction and fault tolerance, that has seen big developments. The first was in 2023. It was the first time that they proved that by using error correction, you can reduce the logical errors. So that was known theoretically, but was the first time that they actually did it in a device. And very quickly, there were, like just 4 logical qubits, but with error suppressed by 800 times. So this is a very big record. And then also the same year, the group, the Quera Harvard MIT group, they had 48 logical qubits from their about 1,000 neutral atom device, which is, we reached the level of logical qubits that exceed the classical simulation. Another new error correcting code. So all these results are using the surface code, which is one that is known. This LDPC code, low density party codes. For there, you can achieve a ratio 1 to 2 physical to logical qubits. However, there is a catch. We cannot do gates yet in this type of experience. So it's just a quantum memory, but it's an impressive progress. And there has been result about how you can create architecture that could use this error correction. That would move a lot all these Q dates or quantum utility dates. And then finally, this result on magic state cultivation, so lower a lot. So this was a last year result. Well, published this year, but was last year, and was when Q date moved from requiring 20 million qubits to requiring 1 million qubits. It was because of this result. It was not because of hardware development. So this shows to you that a factor of 20 in the number of qubits is something that can bring a year ahead or even more the time of quantum utility and Q day. And this is development of the Q day. The first is how many physical qubits in millions. So this was going from here to here was that result, and going from here to here is using these LDPC codes that I told you. So it's quite impressive, the progress that has happened there. And we have a tool. We have developed a tool called Quantum Thread Tracker that has this takes all these different factors into account and can basically give you the Q date or how long it will take you to. If you give me a hardware roadmap, it can tell you when your system will break. However, this is not fully updated. I mean, it needs to be updated. It's an open source tool. Was developed last year, so it has up to these results. Doesn't have these more recent results because but it was made in a modular way, so it can be updated. Yeah, that's one thing to do. And this was a part of a project with a National Energy System Operator and Cambridge consultants that we had. Okay, finally, I managed to have a few minutes for evaluating quantum computers. Okay, so challenges. Why is challenging? Well. There are many reasons why it's challenging. One of the reasons is that you cannot actually, one of the problems with quantum information is that you cannot really observe it. So you cannot go halfway a quantum algorithm, measure what is happening and not disturb it. So if you do that, then you lose the quantum advantage, you lose the properties of the system. So you cannot, inspect it in this way. So that's one of the problems. The other thing is that BQP is not contained in NP, so efficient classical verification is not possible for many of those problems. Quantum hardware is very complex physical systems, and their performance depends on many different factors. And quantum algorithms are affected in complex ways from physical imperfections. And moreover, if you have quantum error correction, this adds another layer of software that needs to be managed, how to do quantum error correction, quantum error detection and correction. I mean, you may have a small circuit that suddenly is amplified by orders of magnitude when you write it in a fault tolerant, and you need to make sure that there is no error in this compilation. Quantum programs are very low level, while optimization and to reach any advantage, they use a lot of optimized compilation tools, and this, of course, there are errors happening there. And finally, proving that you have a quantum advantage is not as simple, is not a simple thing to do. So the first thing that I'm gonna mention a bit is the concept of cryptographic verification of quantum computing. So we cannot, uses the interactive proof system machinery. So here we have the question, if we have a fully, like a classical verifier that wants to prove, want to verify someone that has a quantum device by just interacting, I mean, either completely classically or almost classically. There are some methods. I'm just going to repeat those methods, the idea, and then tell you the developments in this field. So the idea is here that you have like the verifier and prover, and then you can have like different runs of computations and test runs, in such a way that any deviation in the computation that would corrupt the computation would also, with some probability, corrupt the test run. So you can construct those tests in such a way that theoretically you can prove that any deviation in the one might affect the other. And then instead of running the protocol like this, you run it using something called blind quantum computing, where actually you cannot determine whether it's the computation or the test run, and because you cannot separate the two, and any deviation that affects the computation would trigger a test to fail, you can achieve like a verification of quantum computing. That was a general idea, but this is a very high level idea, had a lot of subtlety in this. So just some recent results, we managed to make a different version of this that holds for sampling, so we can verify variation of quantum algorithms in quantum machine learning, which is one of the nice applications. And then there was a version of this protocol that is composable and noise robust, which is also important. And finally, this is while it was theoretical. I mean, recently there have been these 3 different hardware implementations of this. So these are no longer, as long as you can run actual quantum algorithm, which you can only run small types of algorithm, you can also run this type of verifiable versions of the protocol. And this is also due to some theoretical developments that I explained in the last talk 3 years ago, that basically reduced the cost. The initial protocol had a lot of overhead. Now, though, there is no essential overhead. I mean, it's the same requirements as the actual computation run. We've recently wrote a very extensive review on the metrics and benchmark of quantum computers. So this is more about the evaluation of a quantum computer as a hardware, but not only as a hardware. So you have like things like number of usable qubits, connectivity, native gate set. So another thing that plays a role on how you compile a program is that each quantum computer may have different native gates. So one can do control not, one cannot do control not, but there's other 2 qubit gate. Now, if you have an algorithm, you need to transform your algorithm to the native gates of the hardware, and that also, like it's one extra layer. If the native gates are like better, then you may get better performance. And then we have the quality of qubits in terms of time that you can use, and then quality of gates within small circuits, and quality of like performance of a quantum computer within some applications. So these are the different types of metrics. And then we have speed metrics and stability metrics as well. So yeah, I mentioned very briefly the issue of speed. Okay. And maybe conveniently, I end up with just 1 minute to say about the thing that is most interesting to you and I'm less expert of. So this is about quantum software verification. So what is being verified? So you need to verify the circuit equivalence. So you have different circuits, and we want to check that they are equivalent after the optimization, transpilation, or these fault-tolerant transformations that I mentioned when you try to run it in a fault-tolerant way. So you want to check their equivalence. Verified compilation. So we have a logical algorithm that is then transformed to hardware native gates and to the fault-tolerant implementation. And approximate synthesis, you want to bound the error between the theoretical unitary or circuit you want to implement and the transformed. Why is it harder than classical? I kind of said a few things before, but you cannot a quantum state. You cannot inspect it because you will destroy the state if you inspect it. Semantics depends on amplitude and phases and interference. This thing that I told you that things can cancel out. So these are things like these complex amplitudes that you have, like phases in front of it, and this makes the semantics harder. Compilation is heavily approximation based, and there is this thing I already mentioned, that there are enormous transformation because of the fault tolerance. So if you have 100 gates, logical gates, you may need 10 to the 9 to 10 to the 12 physical gates, which it's a mess. And I'm really running, well, I still have 1 minute with no questions, assuming. So main techniques. ZX calculus is a graphical rewriting of quantum circuits that you can map circuits to this graphical calculus that has its own rules, and you can simplify things. Tensor networks, quantum Hor logic, verified compilers, and there is a number of systems, representative systems that I list here. And I think I should stop here. So verification becomes central because quantum computation is transformed continuously because of the optimization that is required and the error correction that also is required to offer any advantage. So yeah, I think that's that. Oh yeah, I have another slide. I forgot about that. Yeah, this is less relevant for you. Here is that this whole have we achieved quantum advantage or not? So there is this a number of claims, but now we have moved from making those claims to actually try to see if we can offer utility, and that will be the final benchmark if we have a quantum advantage or not. But we need to compare not with a classical algorithm we like, but with the best optimized high performance computing implementation and so on. Okay, that's that. Thank you
so much, Petros. Maybe time for one quick question, if anyone in the audience wants to. Dare I mention AI? Dare I mention AI and how it's affecting your field, be it in terms of algorithm design, chip design, anything like that? Have you been touched by AI at all?
Yeah, sure. Oh, well, there are two things: AI for quantum and quantum for AI. So they're both sides. Yes, quantum for AI. I did mention quantum machine learning. There are a lot of things that quantum machine learning may offer advantages compared to like non-quantum machine learning. But yes, machine learning has been used in terms of even for hardware, like optimization, like modeling the noise, the systems, and so on. So it has been used a lot on that. And also there is a competing thing, a negative thing for quantum is that a lot of the problems. So what we're comparing. So now quantum advantage, we need to beat AI as well. So so in a sense, it's that is also some of the applications have there is no so much like point in looking at this because they have kind of been addressed or is like with machine learning methods. So I think this a very quick answer is this. Yeah.
Thank you so much, Petros.
Thanks.